Welcome back to Physics 101, where we will be discussing Chapter 15 on mechanical waves. So our first question would be a biology question on ultrasound imaging. In a typical ultrasound scan, the waves travel through the body's tissue with a speed of 1,500 meter per second. For a good detailed image, the wavelength should be no more than 1.0 millimeter, and we are asked to find what frequency of sound is required for a good scan. To solve this question, we know that the speed of a periodic wave v with a wavelength lambda and a frequency of f is given by v is equals to the frequency times its lambda, and we would be using this equation throughout the problem. Now, throughout the question, we are given the speed of sound of the ultrasonic waves through the body's tissue is 1,500 meters per second, and we know that a good detailed image can be achieved with a wavelength of 1.0 millimeters. Our calculation would look like this. Since sound, including ultrasonic, is a periodic wave, we can use the equation previously discussed. Now, let's plug in our values for v and lambda into the equation, and we would get 1,500 meters per second is equals to 1.0 times 10 to the negative 3 meters, because we would have to convert millimeters into meters. And since we are asked to find the frequency, we can solve this by isolating f, and we would end up with a final answer of 1.5 times 10 to the 6 hertz, and this would give us a good image of the ultrasound. Now, for our second question, we are asked what tension must the rope with a length 2.5 meters and a mass of 0.120 kg be stretched for transverse waves of frequency of 40 Hz to have a wavelength of 0.75 meters. We would again use the same formula since we know that the speed of a periodic wave with wavelength and frequency is given by v is equals to f times lambda. In our equation, we are given the length of the rope, which is 2.5 meters, and its mass, which is 0.12 kilogram, and the frequency of the wave in the rope, which is 40 hertz, and with a wavelength of 0.75 meters. Now, for our calculation, we would first need to find the wave speed, and by substituting our values to our first equation, we would get v is equals to 30 meters per second, which is our wave speed. And now, we would also need to calculate the linear mass density of the rope. And we know that the linear mass density is given by the mass over the length, and it would give us the answer of 0.048 kilogram meter. For our final step, we would need to plug in our values for the wave speed and the linear mass density into our equation number 1 and solve for the tension F as follows. And by isolating our F, we would get the final answer of 43.2 newtons as our tensional force. For our last question, we have a 3.8 meter long steel wire that is fastened into the ceiling, and a 54.0 kilogram object is suspended from the lower end of the wire, and you observe that it takes a transverse pulse 0.0492 seconds to travel from the bottom to the top of the wire, and we are asked to find what is the mass of the wire. We know that the wave in a string speed in terms of the tension force and the mass per unit length mu is given by v is equals to the square root of the force over the mu, our mass per unit length. So now let's draw our free body diagram to have a better understanding. the length of the wire is 3.8 meters, with the mass of the suspended object is equals to 54.0 kilogram, and the wave takes 0.049 seconds to travel from the bottom to the top of the wire. Now, as you can see, this would be our free body diagram. To solve for the mass of the rope, we first need to calculate the wave speed using the distance traveled and the time interval it takes. And this is V is equals to the length over the time, which is 3.8 meters over 0.0492 seconds. And we would have the answer of 77.2 meter per second as our wave speed. Now, we would need to apply Newton's second law to the hanged mass, and we would get the summation of all the forces in the y-axis, and we would have the answer of 529 newtons. Now, we would need to plug in our values for V and F into the equation 1 and solve for mu, and so we would get the answer of 0.089 kilogram meter as our mass per unit length. And now for the final step. We know that the linear mass density is the mass per unit length, which is mass over the length. By isolating m, we would get the mass of the rope. Finally, we plug our values for mu and L into m expression. So we would get m is equals to 0.089 kilogram meter times the length of the rope, which is 3.8 meter, and we would have the final answer of 0.337 kilogram as the mass of our rope. That's all for today. Hope I was able to help with your physics journey. Thank you so much for listening. Till next time.